All right. So hello, everybody. Welcome to, I'm not even sure, I think the fourth meeting of Inland Empire Math Circle. So today we're going to be discussing a very interesting problem. It's called the Koenigsberg Bridge problem. Now it sounds kind of weird, but basically it's a problem about crossing bridges. And we would appreciate if you would turn on your cameras, though obviously it's optional if you don't want to, but we would prefer if you do. And yeah, so why don't we get started? So the Koenigsberg Bridge problem, originally, it was basically this sort of you had a bunch of bridges across islands in a city called Koenigsberg. And the idea was that you had to cross each bridge only once, and you would try to go through every single bridge, cross every single bridge exactly once. And obviously, if you say cross CB, then you can't cross DE right afterwards, right? You have to go from CB to BD or from CB to BA. Now, the idea was that you had to cover every single point, every single bridge on this sort of diagram, but you couldn't cross the same bridge twice. So for example, if I go back to B, I can't go to B, I can't go to BA again. That's, yeah, you can't draw a line over lines you've already drawn. So this is basically just the pretty basic idea. It's a pretty basic idea of Koenigsberg Bridge problem. And so does anyone think they have an idea of how to solve this question right here, this one right here? Now you can start at any points, by the way, any points. We would encourage you to unmute if you would like to answer.
Here, Kimi, do you want to try this problem?
Okay. A to B, a B to C. Oh, no. Go back. It's B to D. No, actually, I want to restart. I don't know what I did. A to E. E to D. D to A.
Yeah, so you have to cross one of the bridges. D to C. Right. Nice.
D to B.
C to B?
C to B. C to D.
Uh-oh.
Oh. Can I wait a second? Can I have a second to think?
Can I try?
Yeah, sure.
Yeah, sure.
B to A.
B to A.
A to E.
A to E.
E to D.
E to D.
Wait, can I ask you a question?
Sure.
Yeah.
At the beginning, can you go back to it?
What do you mean the beginning?
Where I started?
Yeah.
So I went to B to A to E, and E to D.
Yeah.
But can I go D to C and then back to B?
Yeah, so you can cross the same point twice, but you can't cross the same bridge twice. Sorry, I should have made that big for you. So you can go back here.
D to B. B to C.
B to C.
C to D.
All right, nice. Congratulations. That was actually really good. But so why don't we have a look? It's so a lot of times in these kinds of puzzles, you want to sort of quantify, or we're going to try to find a pattern in these puzzles. But because this puzzle seems so sort of It's just, you can't really make numbers on these. So like, it's not really that obvious how you can make numbers on these. So does anyone have any idea of how we can put numbers onto these points? Like, what kind of properties do each of these points have? Like, what property does point C have? Like what, yeah, like what attributes does it have? And how can we, and like numbers that you can put onto point C? Does anyone have any ideas as to what kinds of properties each point has? Hmm. Okay, so okay, maybe that question might have been a bit hard, but why don't we actually have a look at the number of bridges each point has? So how many bridges are attached to, say, point C? Does anyone see how many bridges are attached to this point right here? Oh yeah, so Gavin said 2. So yeah, so it's pretty obvious. It's 2. But, and how many points do you think are attached to point B? How many bridges, sorry? Yeah, 3. So if we just plot out we're just gonna record the point that we started at and the point that we ended at for in terms of the number of bridges that are attached to it. So we start at point B and we end at point B, which both have 3 bridges attached to them, right? Actually, yeah, I think we can record the rest of the bridges. We can just record the number of bridges attached to each point. So we have 2 points with 3 bridges attached and 2 points and 3 points with 2 bridges attached. So I'll just send that into the chat. 3, 3, 2, 2, 2. Actually, no, I'll annotate. Yeah. All right, so let's move on to the second puzzle. So does anyone see how we can do this puzzle?
I see something.
You want to give it a try?
C to A.
C to A.
C to D.
Mm-hmm.
D to A to C, C to B, and then B to A.
And then B to A. All right, congratulations. That was really nice. So again, I'll just record. So you start at a point C, which has 3 bridges attached to it. So we'll just do 3, 3, 2, 2, because there's 2 points with 3 bridges attached, C and A, and 2 points, B and D, which have 2 bridges attached to them. Right. All right, so let's move on to the next puzzle.
Isn't this one the same?
Actually, no, it's not the same.
It has the cross in the middle of the square.
Yeah. So puzzle 1, you didn't have AD. Now it has.
I
AD.
see.
Yeah, that's basically the only difference.
I think it's the same thing, but just we add 2 more steps.
Mm-hmm. Well, actually, does anyone see how many steps any puzzle would take given the number of bridges? Because you can only cross each bridge once. So does anyone see how many steps this would take in total, not depending on the order?
Maybe 7.
Yeah, 7. And can you explain why?
Because there's 7 bridges, so it takes 1 move to move every bridge. So it takes 7 moves to move every 7 bridges.
Yeah, so of course it would take the number of bridges for the number of moves to complete this puzzle. Yeah. So anyway, so does anyone want to see if they can solve this problem, this puzzle?
Here, Lloyd. Lloyd, do you want to try this problem?
Okay.
Ha 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 ha. Can I try?
Yeah, sure.
A to E,
A to E.
E to D,
Mm-hmm.
D to A to B, A to C, A to D.
Oh, C to D.
Yeah, C to D.
Okay.
And then D to B.
All
But
right,
I kind
nice.
of found the same thing where you could go from B to D, and then D to C, and then C back to B.
Yep. So again, I'll record the points. So point A has 3, point B has 3, point C has 2, D has 4, and E has 2. And then starts at point 3.
Are we gonna have points with 5 soon?
I think so.
Oh god. I hope we don't have something crazy like a hexagon thingy.
All right. Let's have a look at puzzle 4. This is interesting. Oh yeah, and remember, there's also an impossible one. So if you actually think it's impossible, or if you think it's possible, we can try.
Olivia, do you want to try answering this question?
No, thanks.
How about
Philip?
Okay. So you would go from D to A.
sorry, did you say B or D?
I said B.
Okay, so B as in like bat.
Boy. Yes.
Okay, good. Okay.
And then A to D.
A to D,
Yes. And then D to C.
B to C,
And then C to E.
E.
And then, oh, actually, I messed up.
All right.
It's impossible.
Well, do you
Yeah.
want to try it one more time, or do you want to just say it's impossible?
I'll try it one more time. From E to C, maybe?
E to C.
Yes. E to C. C to D.
C to D.
D to A.
D to A.
A to B.
A to B.
Yeah, I don't think I can do it.
Yeah, it doesn't seem possible, right? Because, well, if you think about it, it is symmetrical. So starting from B and starting from C is the same thing, right? It's like they're basically the same thing because it's symmetrical and the relationships are the same. So, so starting from any of these outer points is the same. And then there's two possibilities, starting from an outer point or an inner point. And it doesn't seem like starting from either of these is possible.
I knew it was impossible.
Thank you so much for the detailed explanation.
You are welcome, Philip.
That was so very helpful of you.
Okay, thank you, Philip. Gavin, you said you wanted to try. You can try.
B to A.
B to A.
A to D.
A to D.
D to E.
D to E.
E to B.
B to B.
B to C.
B to C.
Yeah, I think that's the the closer you can get. You just have to miss the C to D.
Yes. Yeah. So.
Wait,
Oh, you muted yourself.
is it possible for like C to touch E twice? I mean like C to yeah.
Sorry, I don't think I heard.
Is it actually possible for C to go to E like again when D went to E?
Wait. Sorry, could you repeat that?
I'm just asking something about the puzzle.
Uh-huh. So just so why don't you just like say what you're asking, like D for like the steps of what you're
Like D to E, E to B,
Mhm.
B to C.
Mhm.
And is it possible for C to go to E?
Yeah, it is possible for C to go to E. Yeah, so you can sorry, like I didn't mention this, but you can cross points twice, but you can't cross bridges twice. So like you can't cross the yellow lines basically.
It's impossible, but if we were to actually possible it, I think we need one more.
One more bridge or one more point?
Yeah, I think one or two more. I think one more bridge, because like at E, we could cut off one bridge from A, the A to E bridge, and then connect it from the E to D.
Connect, and then wait, what?
So if there's a bridge between E and A, if we remove that and put it between E and the line between C and D, we could get to C and D, and then it would be almost possible.
Oh, so what you're saying is if we take away the AE line and we just drag it between C and D, it would be possible? Or are you saying if we move another thing to C, straight to C, it would be possible?
I think it would be like removing like. I don't think we can make this possible, because like if we put the E sign, A and E bridge between C and D, it kind of won't work, because we gotta go one half and then the other half.
Yeah, so actually let's think about it like this. What if we just ignored CD? Would that be possible?
Yeah, definitely.
Yeah, it would definitely be possible. So yeah, so but this puzzle here is impossible.
Dude, he's like, no, the computer's like, try something different, but it's impossible. What are we supposed to do? Try something different?
The computer is trolling us.
Is this puzzle like supposed to be impossible, or there's one way, but it's really hard to figure out?
Yeah, why don't we see? So we have a button here, check. Oh yeah, and a purple star means that it's impossible, by the way. It is in fact not possible. And later we will actually see why it is impossible and how we can find out it's impossible before even trying it. But for now,
it's really easy, because you just need to find if it's even, if the number is even.
It actually would be possible if you remove C, the bridge between C and D.
Yeah. So, but for now, let's just record the thing. Also, by the way, Kimmy, you are very correct, but don't spoil it for now. Right? So we'll record that we have 4 points with 3 on them, with 3 bridges, and 1 point with 4 bridges. So we'll just say that, and then impossible. Right? And we'll try one more puzzle.
Ooh, this looks fun.
Yeah, this one is quite complicated looking.
It's pretty difficult.
It kind of looks like the same, but just there's a triangle on the top.
Yeah, but it's also kind of similar to the first puzzle that we did.
Yeah.
Yeah,
just
so
we have the X in the middle.
Yeah,
it looks like a house, a really plain house.
It looks like you know, those cow ranches that have like X's on their door to
Oh,
keep the cow from getting out.
yes. Triangles are in fact a very strong shape in engineering. Okay, but anyway, let's not go on a tangent. Why don't we try this puzzle?
Uh, First thing I was thinking, we could like break this thing up into two pieces.
And yeah, so what do you mean by breaking it up into
Like
two?
we could break the top part of the triangle from the bottom part. Both parts would be possible.
Yeah, but this is more than the sum of its parts. It is emergent. So you can't just break it up. You have to cross every single thing. It is more than the sum of its parts. But that is true.
Even plus even equals odd.
But anyway, so does anyone want to try this puzzle?
This is just weird puzzles.
It is not just weird puzzles. It's actually like originally there was this mathematician who said that it was a weird puzzle that was useless, but they later found out that this later created a whole new a whole new part of math. So it's actually really interesting. You guys should go read into graph theory.
No, but like I don't know what we're learning. First class we were learning about crossing the river or something. And then a few classes later we were talking about the something door, and now we're talking about this puzzle. What are we supposed to get on the topic? Math logics?
Yeah, math logic. First of all, it works on your logic skills, but it also has some individual math subjects. Like the first one, Tower of Hanoi, that was about recursion and pattern finding. The second one was just entirely pattern finding and just logic in general. It wasn't as math based, but it was about logic. The third one was about probability. The doors, that was like additional probability. Yeah, obviously. And this one is about graph theory, and it's also about pattern finding and like how you can prove stuff and quantify something that is so visual.
And when I think it's impossible.
You think it's impossible?
Yeah.
Why don't we see if it's impossible?
Now
It
let's
is
try it.
possible.
What? It's possible? How is that possible?
Yeah, I think why don't we try it? It's like see.
Oh, I see why it's possible. I see. I was too busy looking at the bottom part.
Yeah. So
Is it from E to D and then D to C?
E to D and then D to C.
And then C to F.
Mm-hmm.
F to B. No, F to B, yeah.
Yeah.
No, wait. Oh, wait. B to C. B point to C. C to E. E to B. B to A. B A to E.
Uh-oh.
So that's the problem. You can't fix it.
Because we're almost running out of time, I'm just gonna give you guys a hint. You could start from point A. See what's gonna happen if you start from point A.
Thank you for the hint.
No problem.
Also, you can notice something interesting about point A, and we'll look at that pattern. So does anyone want to try it out with point A?
Oh, I see it. This is such a meme. Oh my god.
Kimmy, if you see it, you can try
A
it.
to B,
A
I
to B,
think. B to F,
B to F,
F to C,
F to C,
C to B,
C to B,
B to E,
B to E,
E to A,
E to A,
A to D, D to E,
E to E,
E to C,
E to C.
and a C to D.
Yeah, congratulations. This one
So
was
hard.
but let's record the points again. So we have 1 point with 2 F, 2 with 4, 3 with 4. B, C, and E both have 4 bridges. Wait, what is both but with 2? I'll have 4 bridges. So we have 4, 4, 4. And then we have 2 with 3, which is A and D.
Okay.
But yeah, so does anyone can everyone go into the chat to see all of the things that we just recorded?
Okay, I'll do it.
Yeah, so there are some nice messages in the way, but we can see that there is. Yeah, so does anyone see a pattern as to where it starts and where it ends?
3, 3, 2, 2, 2, 3, 3, 3, 4, 2, 4, 4, 4, 3, 3. To be exact, I don't see any.
Yeah, so instead of looking at the numbers on top, why don't we look at where the points start? Like, because there is a pretty clear pattern for where the points start and where they end.
On the chat, it says starts at point with 3 and ends at point with 3, starts at point with 3, ends at point with 3. It just...
Well, that is so obvious.
Yeah.
And then the only thing that's weird is it just says, yeah, it's impossible.
Yeah, it's impossible. But yeah, like notice how like it always starts at a point with 3 and ends at a point with 3. And we will see why, but also notice something about the one that is impossible. Notice the number of points that start with 3 compared to the number of points that start with 3 on the other ones.
3, 3, 3, 3, 4.
Which
one is odd? One is odd. The impossible one is odd. And the possible one...
No?
Oh, wait. There is one odd one.
Yeah, but it's actually we should look at the number of points that have 3 bridges attached to them. So remember this this one, which was impossible. The number of bridges that have number of points that have 3 bridges attached to them. How many are there in this diagram compared to the other ones?
Anyway, can I ask a question?
Yeah.
What do we use the Discord server for?
Well, the Discord server is for you to discuss math, but it can also you guys can also just get to know each other, because I think
I know, like I don't see lots of math brains in there. The most I see is just chatting.
Yeah, I mean that's fine as well, but it is a math Discord server. Okay, so so I'll just rewrite these again. We have 3, 3, 2, 2, 2, 3, 3, 2, 2, 3, 3, 2, 4, 2, and then we have 3, 3, 3, 3, 4. So can anyone see a pattern? Because the 3, 3, 3, 3, 4 one was impossible. And does anyone see how this one differs from all of the other ones?
Wait a minute. Is there only one? Is there 3? Is it the only one that has only 3? Oh, it's the only one that has 3 3s.
Oh yeah. So that is actually what it is, but it is the only one that has 4 threes. There are 4 threes there, and
Oh,
all of the other ones have 2 threes. So
Maximus, and then like 3 2s.
yeah, but it's actually mostly about the number of threes that there are. Okay, so now we will see why this happens. So why this pattern exists, that you have to start at a 3, end at a 3, and that there can only be 2 threes, otherwise it'll be impossible.
Could we make a puzzle where there's like 6 3s and then let's see what happens?
6 threes?
Or like 3 3s and then something else? Could we make a puzzle like that?
Yeah, we could probably make a puzzle like that eventually, but
But it would require a lot of scripting or something if we post it online.
Mhm.
No, I mean like creating it for like this class only.
All right. But David will now do some explanation as to why this pattern exists. So I will stop sharing, and David Ma will begin with his excellent explanation.
Hello. Okay. So then, first of all, we have like 3 shapes here, and then basically what I'm gonna do is I'm gonna label like how many lines are connected to certain points. So then for the Koenigsberg Bridge problem. So for the first one, there's 2 lines connected to this dot. For this one here, it has 3 lines. This one here also has 3 lines. I mean 4 lines. 4 lines. 4 lines. 4 lines. 4 lines. 4 lines. And 2 lines. So then, do you see a pattern here? Like, all of these numbers here are basically even numbers. There's no odd numbers here. You know, it's all 4s. There's 5 4s and 2 2s. It's all even numbers. There's no 3, no 5, and other stuff. And we call this kind of shape an Eulerian shape. Now, what's special about an Eulerian shape is that you can basically go from any point on the shape. You could choose any point on the shape, go from that point, and you can manage to trace the whole shape and return to the exact same point. So, for example, if we start from this point here, we go here, 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 and see we return to the exact same spot. That's what's special about the Eulerian shapes. For this one here, see the markup. For this point here, there's 2 lines connected to it. This one here, there's 4 lines. This one here there's 4 lines. 4 lines, 3 lines, and 3 lines. Now we call this shape an semi-Eulerian shape. Now what's special about this shape is that you could there's two odd points on this shape. For example, 3 and 3. Besides the 2 odd number points, all of the other points are even numbered. And then for this kind of shape, you go from one of the odd number points. You trace the shape, and then you'll return to the other knot where there's like an odd number lines connected to it. So, for example, we travel from this dot here. We go here, 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 here. And we started from this point here, right? And eventually we return to this point. So we're gonna return to the exact opposite point where there is an odd number of lines connected to it when we have a semi-Eulerian shape. And for the last one, let's do the markup again. There's three lines here, 3 lines here, 3 lines here, 3 lines here, and then 4 lines here. We call this shape an non-Eulerian shape. For this kind of shape, it has 2 or more. It has 3 or more odd number dots on it, and basically for this one, you can see there's three lines connected dots, which means that it's more than 3, and there's only 1 4. So for this shape, you actually can't connect all of the dots with 1 line because it's a non-Eulerian shape. And yeah, you could try to connect this shape, but then you wouldn't succeed because it's not Eulerian, and it has like 3 or more odd number dots. And that's basically how you identify these shapes. If all of these dots have like even number of lines connected to them, then you can basically go through the whole shape, starting from any point. If it only has like two odd number dots and then the rest is even, you can start from 1 dot and then trace the same shape, and then eventually return to the opposite side of the dot. And then if it's like 3 or more odd number dots, then you can't trace it. It's just impossible. So Kimi, you asked a question. You asked the question of like whether you could create like a shape with 6 dots, has like three lines connected to them, right?
Mm-hmm.
So that's basically 3 or more. That's
That
basically
would be
3 or more.
right?
Yeah, you can't cross it because it's a non-Eulerian shape. Now let's look at some problem sets. This one is a really interesting one because it asks you like you have to go through
Do I have to go through all of these things just to go to the post office?
Yeah.
Oh God.
Now, what we do with these questions is at first, you like this type of question basically asks you, how do you get to the post office in the fastest way? And basically, to get into to do it in the fastest manner, you have to like only cross 1 lane 1 time, right? Because if you cross it two times, it's gonna be you're gonna be slower. So for these type of questions, it's basically asking you, how do we connect all these rows with 1 line without crossing them twice?
Wait, all of these rows, or do we just have to go to the
all of these rows?
Why would we cross all of these rows when we can only cross 1 line and just get to the post office?
Well, imagine if you're imagine if these points
They're
here
exercising
are these points here are like places where people live, right? So so like you go to the post office, you get their like the letters they receive, and then you basically give it to these people that lives on the street. So then you have to like go through all of these points and then return to the post office. That's what you have to do.
Okay, I think that might be impossible.
That's actually not impossible, Kimi. Let's not give up. It's not give up so soon. We could actually like solve this problem.
Oh yeah,
First,
and in this case, you can cross the same road twice for this, just by the way. But you just want it to be as fast as possible. So you shouldn't cross the same road twice, but you can. So of course it's always possible.
Okay.
Yeah.
That is just easy.
all right. So what you do with these kind of problem sets is that you first of all you identify the knots. Like, what do I mean by knots? It's basically like points where you have like one or like two or more than two paths where you could choose to go. So like for this point here, it's a knot because you go here or you could go here, right? This point here, you can also go here or here, here or here. So then that's basically a knot. And then when you go to here, Kimi, tell me why isn't this thing a knot?
Why is this thing a what?
Why isn't this thing a knot?
Oh, because there's only one path. You can only go one path.
Yes, exactly. You can only go from here or here. There's no choice. If there was a road here, you could go here, then it's gonna be a knot. But currently, there's only you can only go from one
Yay, then you
direction.
can go out of the world.
Okay. So how we solve these kind of problems is that we draw the knots, like how they appear on the thing.
Does that mean I could just cross through the board? It doesn't really make sense like this because there's no roads.
And you connect all the dots.
I connect the dots in my old workbook.
Oh, well, we can't make this. Well, we can't go. We can't go through the lines, you know. So if we want to make this shape, we're just gonna have to like go through every line.
Sorry, I'm just not here. Okay. So after we got the knots, we're gonna basically number the number of lines that's connected to it.
Yeah, but how do we even digest it into this thingy? Well, we can't just go through the roads, right? We're not going to just like go through the roads, right?
What do you mean, Kimi?
Like we have this whole thing written out, but the thing already written it out for us. So if we count the lines, we'll only find how many moves it takes, but we don't know how to solve this thing. We're not going to cross through the roads to make this shape, right?
The whole thing about Kimi, like the whole thing about like the Chinese postman problem is that you go across the road. So sorry, a few mistakes here.
Oh, I can go across the road, so I don't have to be on the road, right?
Technically, you do have to be on the road, and I'm gonna explain right now how you actually solve this problem.
Yeah, I'm saying that. Like, why would we just cross the road? It's way easier.
Think about the areas between the roads.
It's like a trick question, all right? Like you have to follow the rules, Kimi. Like,
think about the areas between the roads like blocks, and the postman has to go to every block and every side of every block. It's so you can't really go through a block, basically.
Okay.
All right, so the first thing we do is that we we labeled the number of lanes that's connected to the knot. So this one's 3. This one's 2. This one's 3. This one's 4. 2. 3. 3. And then 3. So something we realized with this thing is that it actually has 3 or more than 3 knots with like odd numbers of lines connected to it. And so typically what we do now is that usually with these kind of problems, like it's uncrossable, right? Because it has like it's a non-Larian shape. But then what we do in this case is that we connect some of the dots to make it crossable. So what do I mean by that is that you could add an extra lane here.
Why would we do that?
Kimi, it's just a problem. It's just a problem set. That's how it works. All right.
Okay.
Like it doesn't make that much sense, but then it's math. You know, we do math here.
Okay.
So what we do now is that we could try and connect different points, and then we connect this point and this point. Now, Kimi, if we connect these 2 points, then what are these numbers gonna change into?
That number would probably be a 5, I think.
You sure?
What? No, like the one that you connected to that was a 3 would turn into a 4.
Yeah.
And then the 4 would, will still be a 4.
This one would also change into a 4, right?
Yeah.
And so now we have we changed the 2 3s into 2 3s into 4s. But then we still have 3 3s left. So what other lane what we're gonna add is here. We're gonna add another lane here.
Okay. That makes one of them 4, and the other one just still 3.
No, the other one also becomes 4 because you see, when we add.
Oh, I see. I thought it was like the whole block inside of it.
So, I missed this. And now there's only 2 3s left.
That's enough.
So, yeah, we could draw a line here to make it like a full Alarian shape, so that we can start at any point on the shape and then finish the whole thing, or we could just do this so it's a semi-Alarian, but then you have to start at this point and then return to this point eventually. So it depends on like whether you want it to be easy or more difficult. But here does Kimi, do you want to try and solve this problem?
Okay.
Just tell me to go from which number to which number.
2. Wait, so I gotta cover all of the things.
Yeah, and remember this is an semi-Eulerian shape, which means that you have to start from an odd number point, and then add an odd number point. So you have to start from 3.
I kind of give up. I can't find anything.
Can you give up?
Yeah, I can't find anything.
Well, let's make it easier for you. How about we connect these 2 points, and then we changed the 3 here into 4 and 4. And that's easier because then you can start at any point.
Oh, that might be fun. 4 to 4.
This 4?
Yeah. And then 4 to 2. 2 to 4. 4 to 4. The bottom 4. And then 4 to 4. And then 4 to 4 again. And then 4 to 4. And then 4 back to 4.
This 4 or this 4?
I would say the left 4. Yeah, the left 4. And then 4 to 4, the top 4. And then 4 to 4, and then 4 to 4, 4 to 2. No. I didn't mean to go from that 4 to the other 4. I want to go down to the right 4.
Like actually, Kimi, like one of the things you did wrong from the beginning was that you see you're supposed to like go from this point and then end at this point, right? Wait.
No, like I was thinking like, could we have that point go all the way to the max right point? Could we go all the way that way?
Yeah, sure.
And then if we go right to that way.
You mean left?
That way. Yeah, left. And then up. And then jump over, use that other one. And then go through the 2. And then 4.
Hold on, Kimi. You finish this problem set. And that's basically how you solve and basically like how you trace a shape without leaving your pencil off from paper. And that's basically the content we covered for today. Does anyone have any questions? Nope. Well,
no.
Thank you for coming to Inland Empire Math Circle for today, and see you guys next time.
Oh yeah, we'll post some discussion questions on. We supposedly will post some discussion questions on Discord and on the Inland Empire Math Circle website. The question board is open for all of you guys to like discuss these discussion questions. But other than that, I think we're done.
Thank you so much. Have a nice day.
Bye. Thank you.
Goodbye.
All right, thank you guys.